Okay, if you've just shown up, just hang out for just a minute. I'm sending out an announcement just to remind everybody that this is going on tonight. So just sit tight for just a minute while I get us started. Okay, so let's go ahead and start. I just sent out a quick announcement to make sure everybody knew that this was going on tonight. Just give me a comment in the questions area if you can hear what's going on, if you can see what's going on, just to confirm. Now we're going to go through 7 topics ranging from gas stoichiometry. We're going to go through some acid-base stuff, some solutions chemistry, a little bit of everything based on the feedback that I got from the discussion board assignment that you had earlier this week. So we're going to start off with gas stoichiometry. Gas stoichiometry is very similar to the stoichiometry that you did for exam 2. We're still going to need 2 things. We're going to need moles. Actually, excuse me, instead of moles, we're working in the gas chapter. So we need liters. This is the only change from what you've done before. We'll need liters instead of moles. Because we've got Avogadro's law, we know that moles are proportional to liters, so we can use liters instead when pulling off the stoichiometry math work. We also need a balanced reaction. Once I can check off both of these, I can do gas stoichiometry. And really all stoichiometry boils down to is predictions. So gas stoichiometry is all about predicting what do I have, what do I need, or what am I going to make. This sample problem says if 2 liters of CH4 is fully reacted, how much water will be produced in liters? Okay, so this is where I'm starting over here. I'm starting with the CH4, and it's asking about water. So how much water, H2O, is going to be produced in liters? It gives me liters to start with, so I can check that off. The other half of what I need is a balanced reaction. Well, just looking at this, I've got 4 H's on the left, but I've only got 2 on the right. So this has not been balanced yet. So I'm going to go in, I'm going to put a blank in each one of these spots so we can balance it. Easiest number to start balancing with is a 1. That gives me 1 times 1. Little 1 in there is unseen for the C. So I've got 1 carbon on this side. Now let's head to the other side. So the product side needs to have 1 carbon also. If I put a 1 here, 1 times 1 gives me 1 carbon. This is a combustion reaction back from exam 2. You don't have to know that for exam 3, but it will be popping up again on the final. So we're going to balance it in the order CHO. So my carbons are done. My hydrogens, 1 times 4, I've got 4 H's. If I go over here, what times 2 is going to give me 4 H's on this side? I'd have to pop a 2 here because it multiplies through. 2 times 2 gives me 4 H's. So now I've got 4 H's on each side. My H's are balanced. Last up is the O's. 1 times 2 plus 2 times 1 gives me a total of 4 oxygens on this side. So that means I need 4 on this side. I need to put something in this blank, multiplies by 2, that gives me that same 4 O's. If I put a 2 here, 2 times 2 gives me 4 O's. So my O's are balanced. So now I've got a balanced reaction. so I can check that off. I've got liters, so I have everything I need to do stoichiometry. So I'm going to start out with what they gave me. In the whole question, there's only one number that they give me, and that's 2 liters of CH4. So I'm going to write 2 liters of CH4. Now this is where having a balanced reaction comes into play. I want to cancel liters of CH4, so I'm going to put that on the bottom. The problem asks me how much water will be produced. So I want to know liters of H2O. And I'm going to get my numbers from the coefficients that are in the balanced reaction. That's why we had to balance it before we started. Look for CH4 in the reaction. 1 is its coefficient. So I'm going to pot up a 1 with the CH4. With the H2O, there's a 2. So I'm going to put a 2 in with the H2O. 2, multiply across the top, times 2, divided by 1, gives me 4 liters of H2O. That would be our final answer, because the question asked for water in liters, and that's what we finished with. So backing up just a few key steps, if we have a problem that's asking us to predict how much will be produced, how much will be used, how much will be consumed, it's all about predictions. That tells us stoichiometry. For gas stoichiometry, we had to have liters and a balanced reaction. Problem gave us liters, but we had to go in and balance the reaction. That was taken care of now. We started out with the only value they gave us. We used the ratio of what we had, CH4, to what we wanted, H2O, multiplied across the top, divided by what's in the bottom, ended up at our final answer. Making sure that we labeled everything so it could cross out what we wanted to cross out and where we wanted to end. So let me get rid of this name tag that I have up here just so we can free up some space. Give me just a second. Okay. So that was one sample problem for gas stoichiometry. Remember, if you have a question, feel free to post it in the questions area, and I'll address those as they come in. Otherwise, we're just going to keep rolling through the review. I have 7 areas that I'm going to go through. This is the first of 7. So if 800 milliliters of hydrogen peroxide gas decomposes, how much oxygen gas will be produced in liters? Okay, this is another gas stoichiometry problem because it says how much gas will be produced. Another prediction. So this is all about stoichiometry. So I need liters and a balanced reaction. So let's check those off one by one. I'm given milliliters. So before we can do this problem, let's go ahead and hop into liters because that's what they want the final answer in. If I have 800 milliliters from module 1, we had our metric conversions. We're going to put the milliliter on the bottom, the liter on the top, millennium, milliliter, think 1,000. So 1,000 mils for every 1 liter. 800 divided by 1,000 times 1 leaves us with 0.8 liters, and this was of hydrogen peroxide. Well, if we're not sure which one of these is hydrogen peroxide, we know that's water, and that's just oxygen, and it gives the hint that hydrogen gas is decomposing. So this is what's breaking up or decomposing, so it's 0.8 liters of H2O2. We can cross off our liters. Those are ready to go. Now I've got to have a balanced reaction. So let's see. We balanced the one up top, so I'm going to run through this one a bit quicker. If I put a 1 here, let's do the H's first. 1 times 2 gives me 2 H's. Hopping over to the other side, if I want 2 H's on this side, I'll have to put a 1 in front of this also. Now to wrap this up, I need something that'll go in this blank. I've got 2 oxygens on this side, so on this side I need 2 also. 1 times 1 gives me one of those two oxygens. So over here, I need something that I can put here to get my last oxygen I need on this side. So let's put 1/2. 1/2 times 2 gives me that extra oxygen I need. So now I've got 2 oxygens on this side total and 2 oxygens on this side total. Now, if you remember from last exam's material, I can't leave that little half there, so I'm going to have to multiply everything by 2 to get rid of the half. So now we've got a balanced set of coefficients, and now I've got a balanced reaction. Now we're ready to do the stoichiometry that's all about predicting how much is going to be produced. So we'll start again, same as we did up here, with the only number that's given, only we'll start with it in liters because it wants the final answer in liters. So I'm going to start down here with 0.8 liters of H2O2. It wants me to predict how much oxygen gas will be produced in liters. So I'm not interested in the H2O, I'm interested in the O2. So I'm going to come over here. Just like in the previous problem, I'm going to set this up so I can cancel out what I started with and end in the unit that I want. I want to cancel liters of H2O2, and I want to end in liters of O2 because I'm looking for oxygen gas. I get my coefficients from the balanced reaction. H2O2 has a coefficient of 2. O2 has a coefficient of 1. 0.8 times 1 divided by 2, our unit cancels, and we get 0.4 liters of O2. Final answer, because it's asking for liters of oxygen gas. Are there any questions here? If you get any questions, it can be, where did you get that 1,000 from? Or how do you know why to put the 1 on top and the 2 on bottom on that last step that you did? Feel free to stop me at any point and ask questions. Okay, next up. We're going to move into gases for a little bit. We're going to talk ideal gases and kinetic molecular theory. So let's see what we've got. We're going to start out with a gas particle. This gas particle is assumed to have negligible volume. What that means is this gas particle, if it's going to be an ideal gas and follow the rules of KMT, kinetic molecular theory, this gas particle is so far away from its next neighbor that the space this gas particle takes up and the space this gas particle takes up is pretty much negligible, which means that these take up pretty much 0 volume. So we're under the assumption that ideal gases take up no space. Remember, these are assumptions, so they're not absolute truth. They're just assumptions that make the theory work, that gases will follow these general behaviors. And to answer your question, Hannah, the previous problem that we did, yes, you can start balancing with a 2 instead of a 1, but it's usually a safe bet to just start with a 1 and work your way up, because if we had to start with a 17 and we didn't know it, things could get ugly pretty quick. So better to start simple. But good question. Okay, so let's get back to our ideal gases and our KMT. We're assuming they take up no space. We're also going to say that this gas particle has to travel around and go from place A to place B. When we think about wind, we think about this air that just kind of moves around and swirls. This is not the case. Air does not swirl around, gas doesn't swirl around. If it's an ideal gas, it's going to travel in straight paths, and when it collides with something, elastically, it's going to bounce right off of it and travel right away. So it's going to travel in perfectly linear paths. We're also going to make the assumption that if I have a gas particle here and a gas particle here, there is going to be no force of attraction or repulsion. They're not even going to interact. Now, part of that is, remember we said gas particles are really far apart? They're not going to interact because they're so far apart. That's why this assumption, really works and really pans out for ideal gases. We assume they don't interact, and that's just because they're nowhere near each other. So let's back this up a minute. When we're thinking about ideal gases, I have gas particles. If you thought of two ants that were at Walmart, one's at checkout line number 1, one's at checkout line number 20, they're separated by such a large distance that the space that these gas particles take up, essentially zero. They travel in straight paths, and they're not attracting or repelling one another. To wrap this up, we also have the relationship for gas particles that temperature in Kelvin, or absolute temperature, is related to average kinetic energy. This is the E of motion, energy of motion. So if we increase the temperature, we're going to increase the energy of motion. Or if we put this into English, if we heat up a gas sample with a higher energy of motion, that gas sample is going to have little particles that are zipping around faster. So let's go down and see if we can apply this to this sample problem. It says, given the following gas samples, I have two gas samples, gas sample A, gas sample B. A has 2 moles of gas at a higher temperature in 1 liter balloon. Gas mixture B has a little less gas at a lower temperature in the same size balloon. And it asks which is at a higher pressure. Okay, so let's think about this. How do gas particles cause pressure? Well, let's pretend that the edge of this paper is a wall. If I'm a gas particle, the way I cause pressure is by striking that wall. Well, we can think of a few ways that we could increase that gas pressure because we're looking for higher gas pressure. One way to increase gas pressure is to not have one particle, but have 2 particles. So we could say the more particles there are, the more that are striking the walls, the higher the pressure is going to be. You can also think about temperature. We said when I increase temperature, I increase the energy of motion. So if I increase the temperature of these gas particles that are striking the wall, they're going to hit even faster. The faster they hit, the more pressure there is going up against that wall. So let's look at our samples. Let's see, A has more particles because it has more moles. Moles represent the number of gas particles we have. So A has half a mole more particles. We can also look at temperature. When you compare the temperature, A has a higher temperature, so it has more energy of motion. These particles are hitting harder against the walls of the container. So it also has higher T. So when you put these two together, they both point towards A having the higher pressure. The second question is, which contains more gas particles? Well, if you look at the moles, moles represent number of particles. A has 2 moles of gas particles. B has only 1.5 moles of gas particles. So that means with more moles, A has more gas particles. So more moles, more particles. And I will make this available afterwards, both in video, and I will also post this sheet that I'm jotting down on right now. So we'd say that A has more particles overall. Last one says, which contains faster moving gas particles? Well, up when we talked about ideal gases in KMT, the one that has the temperature in Kelvin that's higher is going to be the one that has the higher average kinetic energy or energy of motion. Because as temperature increases, energy of motion increases. So if I'm looking for the faster moving particles, I want the one with the higher temperature. So AAA, A for the first, second, and third answer, I have faster moving particles because I have higher T, higher temperature. Okay, I'm going to give you guys a chance to post any questions that you have on what just happened. We can refer to these as question I, or I, 1, 2, or 3. So if you have a question on any one of these 3 parts, feel free to ask it. I'm going to give you about 30 seconds to post one, and then I'm going to move on to our next topic. Okay, you all are pretty quiet tonight. Let's move on then. Next question is going to deal with precipitation reactions and net ionic equations. Okay. First off, precipitation reactions are going to take aqueous plus aqueous, and they're going to make a solid. So I have 2 dissolved solutions. When I put them together, we get a solid out. The solid is the precipitate. So this is my precipitate, whatever solid forms. If no solid forms, that means I had no reaction and no precipitate formed. So in the sample question, it says if PbC2H3O22 and Na2SO4 are mixed, will a precipitate form? And if one forms, write out the net ionic equation. So let's take a look at this. This reaction is going to set up a lot, well, pretty much the same way as a double replacement or double displacement reaction. So let's write it out. Pb C2H3O2, there's 2 of those, plus Na2SO4. It's going to go to, let's see, these are going to flip. So my Pb is going to be paired with my SO4. And I've got 2 NAs and 2 acetates. Each sodium, this is in group 1 on the periodic table, so it has a +1 charge. Each C2H3O2, this is an acetate. That was on your list of polyatomic ions to memorize from our last exam. Acetates have a -1 charge. So I'm going to take a +1 sodium and a -1 acetate, and I'll get Na C2H3O2. Now I'm not going to balance this yet, because really I'm just looking to see if a precipitate forms. Now what we did is we performed a double replacement reaction. I took the first part of each of these 2 formulas and we swapped them out. So then when we get to the other side, Pb was paired with acetate, but in the product side, Pb is paired with the sulfate. In the reactant side, sodium was paired with the sulfate, but it switches, and then the product side, sodium is paired with the acetate. So they traded pairs. So it wants us to predict if a precipitate is formed. It's going to be either this or this. So let's go down to our solubility rules. So steps in deciding if you have a precipitate are: write out your reaction with a double replacement where you have a swap, pay special attention to the products, then come down here and look at your solubility table. I will provide this on the exam. So it says all nitrate, acetate, or chlorate salts, and you'll write the word, since these are soluble compounds, you can tag on are soluble. So all nitrate, acetate, or chlorate salts are soluble. Well, if you look up here, this contains acetate. This is a acetate salt, so it's going to be soluble If it's soluble, it dissolves, which means it would be aqueous. It's not going to be our solid if it's capable of dissolving and if it's going to be aqueous. So that's not going to be our precipitate. So let's go over here. Sulfate, SO4. Now it doesn't say sulfate anywhere in the problem. I've got to know that SO4 is sulfate from our list of polyatomics back from exam 2. So sulfate, this guy right here, and just as a refresher, sulfate is SO42 minus, nitrate is NO3 minus, acetate C2H3O2 minus, and chlorate ClO3 minus. So when I look at the sulfate salts, it says sulfate salts are soluble, but there are some exceptions. And the exceptions, these right here, only apply to sulfate salts in the same way that these exceptions only apply to chloride, bromides, and iodides. Well, for sulfate salts, if my sulfate is paired with a silver, Ag, Hg, mercury, Pb, lead, Ca, calcium, Sr, strontium, or Ba, barium, if my sulfate's paired with any one of these, then it's an exception and it'll be insoluble. So let's look at our salt. It's PbSO4. So I have a sulfate, but it's paired with a Pb, and because I have an exception, this is not soluble, so I'm going to give it an S. The S makes it a solid. So this PbSO4 is my precipitate. So now we can go ahead and look at the shortcut for writing the net ionic equation. I'm going to focus for the net ionic equation on just this part, because in a precipitation reaction, this is really where all the interesting chemistry is happening. So I'm going to start out in writing the net ionic and drawing an arrow. On the right side of the arrow, this is where my precipitate goes. And my precipitate is PbSO4 with a solid. Because I'm making a solid, I'm making a precipitate. Then on the left-hand side are the components that make it up. So there's a Pb, and there's just one of them. There's a little understood one to be here. And there's an SO4. So Pb plus SO4. SO4, just knowing this from our last exam, has a 2- charge. So if this was going to balance it, if that's 2-, then this has to be 2+. Our pattern for precipitation reactions were aqueous plus aqueous makes a solid. So Pb2+ is going to be aqueous. So is SO4 2-, the sulfate. So I get aqueous plus aqueous yields a solid. The solids are precipitate, and our net ionic equation just describes the pieces that make up the solid or the precipitate. Okay, any questions on that before we move on? I'll give you about 30 seconds to a minute to post any questions that you have, and then we'll move on to topic number 4. We're doing pretty good on time. We've got 7 topics to cover. Okay, don't be surprised if I get disconnected at any point. There's a wicked thunderstorm that's moving through Morrisville. Okay, no questions, so I'm going to keep rolling through this. We've got a little more on solution chemistry to do. So topic number 4 is going to be the language of solutions and the language of electrolytes. So first off, what's in a solution? So if I have a solution, we're going to have a mixture. We've got to have 2 or more components, or 2 or more substances. That's what's going to make it a mixture. And these are going to have to be homogeneous. So if they're homogeneous, that means it's uniform all the way through. So let's put some water in here, because this is going to be an aqueous solution. And in my solution, I'm going to have solvent and solute. Solvent is going to be the biggest component. So in this case, my solvent for an aqueous solution is going to be water, because aqueous means dissolved in water. So solvent equals H2O. And let's say that this is salt water. If it was ocean salt water, then it would contain NaCl, which is salt. It would contain some calcium salts. It would contain some fish poo. There would be all kinds of stuff in there. It would contain a lot of different components. Seawater is pretty homogeneous. We're looking at an aqueous solution. Our solutes are going to be the smaller components. So in this case, NaCl is a solute because there's salt in there, but not as much as we have water. Water is the biggest component in salt water, so it's our solvent. NaCl is our solute. If we were looking at, say, Bojangles iced tea, Bojangles iced tea is about 10% sugar. It's about 90% water. So in the case of Bojangles tea, 90% water, water is our solvent, 10% smaller component is sugar, so sugar is our solute. When we talk concentration, think about how much is packed into a given area. I want you to think about something. If I have concentrated orange juice versus, we'll call it drinkable orange juice. So I can have a big glass of drinkable orange juice that I pour out of a carton that I get out of the fridge. I can also have, from the freezer section of the grocery store, one of those canisters that contains grape juice concentrate that's frozen. Now, concentrated OJ contains less water, whereas drinkable OJ contains more water. Another word for drinkable in this case is dilute. It's been diluted with more water, more solvent. For my concentrated form, I have less water. That means pound for pound, I've got more solute in my concentrated OJ. I've got less solute pound for pound in my drinkable OJ. So if I say something is concentrated, concentrated means less solvent, but more solute. If I look at a more dilute solution, that would mean more solvent, but less solute. Okay, now moving on, we've also got electrolytes. When you see electrolytes, you probably think sports drinks or think Gatorade, something along those lines. An electrolyte is really an ion or a charged particle, charged molecule that's going to show up in a solution. So if we have something like NaCl, or we have something like CO2, we have to be able to look at these formulas, decide which is going to be an electrolyte versus which is going to be a non-electrolyte. Electrolyte solutions are going to conduct electricity because they have ions in solution that are capable of carrying that electricity throughout the solution. For non-electrolyte solutions, they're not going to conduct electricity. So we've got a choice here. I'm going to pick this as my electrolyte, NaCl. The way that you spot an electrolyte is it has to be a soluble salt. Soluble salts just meaning this salt will dissolve, and salt, or ionic compound, meaning that when it dissolves, it's going to release ions into solution. The way we spot these ionic compounds is they're going to contain a metal and or a polyatomic ion. So just backtracking, if I'm going to have a solution that contains an electrolyte, which means it will conduct electricity, I'm looking for a soluble salt, a salt that will dissolve. It's an ionic compound, and we spotted these because they contain a metal or a polyatomic ion. So looking at this formula, Na is on the left side of the periodic table. It's over here. Anything on the left side of the table is going to be a metal. Since it has a metal, it's a salt, it's an ionic compound, and we're looking at an electrolyte when we look at something like NaCl that's aqueous because we've got salt water. If I look at CO2, there's no metal here, there's no polyatomic ion here. These are all nonmetals. Chances are, if I have a substance that's made up of all nonmetals, it's going to be a non-electrolyte. So think of a solution where I have all nonmetals dissolved, something like C6H12O6, a glucose solution that's aqueous. It's dissolved in water, but it's all nonmetals. Being on all nonmetals, it's a non-electrolyte, and a sugar water solution is not going to conduct electricity. So we just went over what is an electrolyte, and electrolyte solutions conduct electricity. Non-electrolyte solutions don't. We decide what's an electrolyte or what's a non-electrolyte based on what it's composed of. All nonmetals, non-electrolyte. Contains a metal or polyatomic, it's an electrolyte. Okay, any questions on that one before we move on? So take a minute, chew on that. About 1 minute, and then we're going to go ahead with topic number 5. Okay. I'm going to keep moving with our next topic here. Topic number 5 is predictions and gas laws. Okay, so this was all about deciding first off, what kind of problem do we have? Because with gas laws, part of the hard part was making sure we knew what to use and when to use it. So we had a couple of different gas laws, and they had different purposes. Let's scoot this over a bit. If I have changing conditions, I'm looking for keywords like something doubles, something triples. Initially we had this, later we had this. If you have a sense of before and after, then I've got changing conditions. For static conditions, static means it's not going anywhere. Conditions are staying pretty much stable. So I'm going to have a different approach if I'm solving a changing conditions problem or if I'm solving a static conditions problem. Let's write down the cases that we're going to see. If I have a changing conditions problem, that's where I'm going to use, make some room over here, either Boyle's law, P1V1 equals P2V2. Changing conditions, I'd use Boyle's relating pressure and volume. Whenever you see P1 and P2, this is pressure before and pressure after. Volume before and volume after, implying we have some kind of change that's taking place. For Charles' law, V1 over T1 equals V2 over T2. And again, we get that 1s versus 2s, befores and afters. And last one, N1 over V1 equals N2 over V2. Relating moles, N, and V volume, we got 1s and 2s for befores and afters. So all of these you would use if you had a problem that implied that you had something happening and something changing. For static conditions problems, we can look to use PV equals nRT, where R equals 0.0821 liters, atmospheres, moles, Kelvin. So that is a really intense unit right there. But this is just a constant. It's a constant that I'm going to give you. And looking at static conditions, there are no 1s and 2s because there are no befores and afters like we had over here. Static conditions means that we've got one pressure, one volume, one moles, the R is a constant, and T is temperature. So if we know all but one missing piece, we can solve for that missing piece. So let's take a look, and I want you guys to post in the questions section. 2 moles of a gas sample is held at a temperature of 200 K in a 4-liter bottle. If the sample is heated to twice its original temperature, what is the volume of this gas sample? Would we use equation 1, equation 2, or equation 3? Which one of these 3 equations am I going to use for this problem? I'll give you a hint. We've got P, V, N, and T, pressure, volume, moles, and temperature. Circle the 2 of these that are given in this problem that you're actually going to use. And go ahead and post it in the questions area once you've decided which of these 3 equations you think we should use to solve the problem. I'm going to give you a minute to decide. Go ahead and post when you're ready which of the 3 equations we're going to use to approach this problem, and then we'll work it through. Okay, so Mary Lou's saying use equation 2. If anybody buys that, you can +1 her answer. All right, so we're getting some agreement for Mary Lou's answer, and you know what? I'm going to go ahead and +1 that. Oh, you know what? As a presenter, I can't +1 it, but I would if I could, because you're right. So we are going to use equation 2 because it relates volume and temperature. And if you read through the problem, they give me temperature and volume, and they say that if the sample is heated to twice its original temperature, what's the new volume? So I'm relating volumes and temperatures. Yeah, that's right, Hannah. We're doing volumes and temperatures with equation 2. So here we go. We've got to label things. 1 minute before, 2 minutes after, so let's go ahead and write it down. V1, T1, V2, and T2. These are befores, these are afters. We're just going to label it all before we put it in. Now, it says 2 moles of a gas sample is held at a temperature of 200 K. Well, that sounds like where it starts. So my T1 is 200 K. It's in a 4-liter bottle. So my volume is 4 liters. If this sample is heated to twice its original temperature, so that means that if I started at 200 K, my T2 where I end up is going to be twice as big. So it'll be 400 K. It says, what is the volume of this gas sample after it's heated up? So that means my V2, I don't know. So that must be what I'm solving for. So now I can go in and start plugging things in. V1, 4 liters. T1, 200 K. V2, I don't know, so I'm just going to put V2 in and I'll solve for it. and T2 is 400K. We've got to get V2 by itself. The way we're going to get that done is by multiplying both sides by 400K. My unit of Kelvin cancels off totally on the right-hand side, leaving V2 by itself. 400 times 4 divided by 200, that gives me 8. The only unit that didn't cancel is the liter, which makes sense because I was solving for a volume. So 8 liters was my final answer. Let's make sure this makes sense. If I increase the temperature, my volume should increase also, because Charles' law says that temperature and volume are directly related. As one goes up, the other goes up. So if we heat up our sample to twice its original temperature, that means I'm increasing T, my volume should increase also. I doubled temperature, so I doubled the volume, because the volume went from 4 liters to 8 liters. So our answer is correct. Okay, just to recap, in solving a gas law problem, decide if it's changing or static. If it's changing, you have to decide which 2 variables we'd be using. This problem focused on V and T, so I'll be using Charles' law, V1 over T1 equals V2 over T2. We've labeled everything, we plugged it in, we solved for our unknown, and then we made sure that it actually made sense. Okay, let's go to a static conditions problem. So our static conditions problem says, what's the pressure of a 2 mole of a gas held in a 4-liter container at 400K? Okay, it doesn't say anywhere in here anything about heating it up or changing the conditions, doubling, tripling, halving, nothing like that. There's no before and after. That's why it's a static conditions problem. So if I'm going to use a static conditions equation, I'm going to use PV equals nRT. So let's go ahead and start labeling what should go in here. Hold on, get a little stick to the paper here. Okay. So let's label P, V, N, and T. R is just given as a constant up top, so we don't need to label that. So the problem says, what's the pressure? So I don't know P, so that's what I'll be solving for. My volume is given in liters, 4 liters. My N is going to be my moles, so I've got 2 moles of gas. And my temperature is 400K. Now before I go any further, I'm going to double check something. If I'm working any gas laws problem, I need to make sure that I'm in Kelvin. If this problem hadn't given me my Kelvin in our first problem, we would have had to convert to it. In my second problem, if they had given me degrees Celsius instead, I would have had to convert to Kelvin before we start. Why? Because my units in my pressure, volume, moles, and temperature need to match the units that are in my R. So volume needs to be in liters. Pressure, when we solve for it, is going to be in atmospheres. N is in moles. And T is going to be in terms of Kelvin. So let's go ahead and fill everything in just to see where it all falls. I'm solving for P. V is 4 liters. N is 2 moles. R is 0.0821 with that beastly unit on the end, liters, atmospheres, mole, Kelvin. And then our temperature was 400K. Okay, so we've got to solve for P. I'll give you a hint. As long as your units are matching up to what's in the units in R, we can clean this up a little bit and make it easier to look at. So P, let's just look at the numbers, times 4 equals 2 times 0.0821 times 400. We've got to get the P by itself. We're going to do that by dividing both sides by 4. Cancels out on the left-hand side. And on the right-hand side, we've got to multiply what's in the top, divide by what's in the bottom. So let's try this out. Well, my phone has died, so there's not going to be any using Siri for that. So give me a second. We're going to pull out a calculator, and we're going to take 2 times 0.0821 times 400 divided by 4. And I get P equals 16.42. Now, over in the comments section, go ahead and post what the unit on this pressure should be. So based on what we just talked about units, what should the unit on my final answer be? I'll give you a hint. It's going to be one of the units that shows up in R. Should I be in liters, atmospheres, moles, or Kelvin? Okay, bingo. So it is atmospheres. Good job, Mary Lou. So ATM is a unit of pressure. So my answer is going to be 16.42 ATMs. That seems like an ugly number. It's not something nice and round like 2 moles or 4 liters or 400 K. Don't second guess yourself on an exam if you don't get a pretty answer to finish with, because not all answers are pretty. Okay, we've got about 6 minutes, so I'm going to try to wrap up and go through these last 2 topics. If we run a little bit late, that's okay. I just want to make sure we cover all of our topics here. Okay, topic 6, acidity, pH, hydronium, and hydroxide. First off, hydronium, very good to know, is H3O+. Hydroxide is OH-. Now, when we look at acids, acids tend to have an H out front, and they're paired with something. We'll just call it X in this case. So if I have HCl, that's hydrochloric acid. If I have HBr, hydrobromic acid, what do they both have in common? They're both acids, and they both have this H out front. Acids have a job. Acids release H+, or acids release protons in solution. So if this marker was an acid, the cap would be its proton. Its whole job in life would be to give away its proton to something else. We have to have something catch that proton, though. Whatever catches the proton that the acid releases is going to be a base. So we could say bases. I don't know if you can hear the thunder right now, but it's pretty wicked over here. Bases are going to accept protons in the same way that acids are releasing protons. We mentioned hydronium and hydroxide at the beginning. Hydronium we associate with acids. So we could say as acidity goes up, we can think of H+ going up. So we're going to have more protons because acids are releasing protons. We're going to have more hydronium because hydronium is associated with acidity. More hydronium, more acidic. Now, if we look at the same behavior down here, bases are going to accept protons. So if things are going to become more basic, then that means I would have lower H+. That would mean I would have lower H3O+, because you can't be acidic and basic at the same time. You're either one or the other. So acidity means high protons, high H+. If I have high basicity, or something that's more basic, then I'm going to have less protons, less hydronium, but I will have more hydroxide. I associate hydroxides with bases. Bases accept protons, and bases generate more OH minus in solution. Acids release protons, acids increase the H3O plus in solution. So all good relationships to know here. So going down here, we're going to review two things really quick. The review of acid-base behavior and also the pH scale. Let's say I have something like HF in solution. I've got an acid. If I have HF and acid, then that acid's job is to release a proton. I'm going to release that H+. What's left after HF releases the H+? I'll have F-. So it releases an H+ because it's an acid and leaves behind its conjugate base. If you look at the difference between these two only differ by a single proton, a single H+. This one has the H+, this one doesn't. Because they differ only by an H+, they're a conjugate acid-base pair. The one that has the H is the conjugate acid. The one that doesn't is the conjugate base. Now, going down here, one last thing to review on this area. I've got a scale going from 0 to 14. The halfway point between 0 and 14 is 7. This is going to be our pH scale. 7 and exactly 7 is going to be neutral. Not 7.1, not 6.9, exactly 7 is neutral. Because it's our halfway point between being acidic and basic. Anything 0 to 7 is going to be acidic. Anything 7 to 14 is basic. 7 itself is neutral. Going from, say, pH 3 to pH 4, there's a 10-fold difference in acidity when you jump 1 pH unit. So going towards 0, we get more acidic. So we would say something at pH 3 is 10 times more acidic than something at pH 4. Shift 1 unit and you go 10 times more acidic as long as you're dropping in pH. And that multiplies. If we went from 4 all the way down to 2, we would be going 2 pH units. So just going 1 unit, this gets 10 times more acidic. Going another pH unit, it gets 10 times more acidic. So 10 times 10 means if I drop from pH 4 all the way down to pH 2, 10 times 10, it's 100 times more acidic down here than it is up here. So every change in pH unit is another factor of 10, another multiplier of 10, more or less acidic. Okay, last topic, where hopefully I'll still be online at the end of this, as long as my internet holds out. Let's go AT&T Uverse. I do give you a hint here. Know your strong acids and bases off the list in your PowerPoint notes. There is a big payoff for knowing the strong acids and the strong bases. Memorize those lists, because if you know the strong acids off your list, everything else is weak by default. If you know the strong bases off the list, then you don't have to memorize the weak ones. You'll know those by default if they're not on your list. Okay, wrapping this up, we're going to do a couple of calculations with acids and bases. This is our last topic of the evening. And we're going to look at pH calculations based on hydroxide or hydronium concentration. So there are a couple of things we're going to use here. We can use the equation H plus times OH minus equals 1 times 10 to the minus 14th, where if you'd like, remember H plus, mention this in the notes, you can pretty much treat it as H3O plus. So you could say H3O plus or H plus times hydroxide equals 1 times 10 to the minus 14th. This is one of the two equations we're going to use the most. The other would be pH equals negative log of H plus. So let's tackle this first problem. It says, what is the pH of a solution of HBr? HBr is a strong acid. Being a strong acid, it's going to release its proton completely. My cat is losing its mind. Hold on 1 minute. All right, there's a family of tree frogs climbing my window, and he's going bonkers. Okay, so HBr is a strong acid. It's going to dissociate completely. And we said earlier in this review that the job of an acid, if we write this out, is to give away its proton. So HBr is going to give away an H plus, a proton. What's going to be left over is Br minus. And it says that I have 0.00004 molar of my HBr. For every 1 HBr, I've got 1 H plus. My goal here is to find the pH. And if I want pH, I need to know something about H plus. Now, since this is a 1-to-1 ratio, if I have 0.00004 molar here, once it breaks up, I'll have 0.00004 molar here. It's going to be the same concentration for each since it has a 1-to-1 ratio. Now I know the concentration of my H plus, so I have all that I need here to use the pH equation. pH is going to be the negative log of 0.00004. So let's switch over. I'm going to screen share with this. Give me just a moment here. And I'm going to plug this into my Google calculator as negative log of 0.00004. Let's see what we get. I get about 4.4. Now let's make sure this makes sense. Let's flip back over to our paper. My pH is 4.4. Thinking back to the pH scale, 0 to 14, 7 was in the middle. Anything from 0 to 7 was acidic, so this falls in the acidic range, and I was calculating the pH for an acidic solution. So this is right where it should be, being an acid solution. Remember, stop me at any time if you have any questions on where any of this comes from. Second problem is also asking for pH, but it's asking for the pH of a solution with an H3O plus concentration of 0.001. Now, remember we said that H3O plus pretty much treat like H plus. So if I have a solution where I already know the H plus concentration, that's why we went through this step up here. If I can find the H plus concentration, I can get the pH. pH is the negative log of H plus concentration. So in this case, my H plus concentration is 0.001. So pH is going to equal the negative log of 0.001. Somebody go ahead and tap this out on your calculator if you've got it, and let me know what you get for your final pH. What should be the pH of this solution? And when you get it, is it acidic or basic? So again, the question, type it into your calculator, see what you get for a pH, and is that pH acidic or basic? Okay, so I'm getting acidic from Mary Lou, and I'll buy that. When you type this in, the negative log of 0.001, the pH should equal 3. And 3 is less than 7. Being less than 7, that makes this an acidic solution.